So we will begin the nuclei. First, the nucleus. We understand about the nucleus. The nucleus has positive charge, which contains extremely dense particles, and have an overall size smaller than atom. So generally, if we need the order, the nucleus order is 10 power minus 15 meters. 10 power minus 15 meters, and the atom order is 10 power minus 10 meters. 10 power minus 10 meters. So the nucleus contains it contains protons and neutrons. And they collectively called as nucleons. They commonly called as nucleons. And we know that mass of neutron is slightly more than that of proton. Mass of neutron is slightly more than that of proton. And we know that mass of neutron equivalent to 1.6749 into 10 power minus 27 kilograms. And mass of proton equal to 1.6726 into 10 power minus 27 kilograms. And we know that mass of proton is also equal to 1836, exactly speaking 1836, or nearly 1840 times the mass of electron, where we refer the Me is the mass of electron. So we know its value 9.1 into 10 power minus 31 kilograms. So 10 power, so this is 9.1 into 10 power minus 31 kilograms. So we know that mass of electron is 9.1 into 10 power minus 31 electron. So after that, we used to think of 1 AMU. So 1 AMU is nothing but 1 atomic mass unit. We will call it as 1 atomic mass unit. So that equivalent to 1 by 12, 1 by 12. So this is mass of carbon 12 atom, 6 carbon 12 atom at rest in ground state. So generally this 1 AMU is also symbolized as 1U, 1 atomic mass unit equivalent to it is symbolized 1U. So that equal to 1.66 into 10 power minus 27 kilograms. And we need to know the symbols of the nucleons and as well as atomic weight and mass number. Generally, we used to write ZXA. So Z is nothing but this is the atomic number, and A will be mass number. And X is chemical name. So generally we used to take this is the chemical name. So chemical name of the given material. And we know that A equivalent to Z plus N. Z plus N. Okay, so here Z is nothing but this is the number of protons. So this is the number of protons are that equivalent to number of electrons. Number of protons are that equivalent to number of electrons. Z is nothing but atomic number that equal to number of protons. Number of protons are that equal to number of neutrons. And also we are taking capital N. Capital N is nothing but total number of neutrons. Total number of neutrons. First, before starting the nuclei, so first we need to learn about the basics and we need to recall about isotopes. So first we will learn about isotopes. So isotopes means the nuclei have same number of protons but different number of neutrons. But different number of neutrons. For example, we are taking 1H1 and as well 1H2 and as well 1H3. So we will see that same atomic numbers we have. So Z is same. Z is nothing but same number of protons. Z is nothing but same number of protons. So we will see different number of neutrons. So we used to call that is the isotopes. And next we are taking isotones. So isotones means the nuclei have same number of neutrons, but different number of protons. So different number of protons means definitely they are having different atomic number. So that is the logic. So here different atomic number means they have different set. Example I'm taking 6 carbon 14, or we will take 8 oxygen 16, or we will take 9 fluorine 17. 9 fluorine 17 we used to take. So this is the example for isotones. So next we will think of isobars. We used to think of isobars. So isobars means the nuclei having same mass number. For example, I'm taking 6 carbon 16 and 7 nitrogen 16 and 8 oxygen 16. So this is called as isobars. And the last thing is nuclear spin. So generally, when we think of nucleons, that is the protons and neutrons, inside a nucleus. The protons and neutrons inside a nucleus have internal spin have internal spin and angular momentum. So the resultant of all these, is called as nuclear spin. All these called as nuclear spin. So these are the basics of nuclei. So after thinking of the basics of the nucleus, so let us think a while about nuclear forces. Nuclear forces. Nuclear forces. So the forces that bind the nucleons, that is protons and neutrons, that bind the protons and neutrons together in the nucleus. Despite of Coulombic repulsion between protons. Is called as nuclear forces. So generally, between the protons and protons, generally we have the repulsion. So even though we are having repulsive forces between the protons, so there might be some internal forces inside the nucleus, so which may be present between the protons, or between the protons and neutrons, or between the neutrons and neutrons. So that kind of force which tries to bind the nucleons is called as nuclear force. So we have some important properties for the nuclear force. So the first one is nuclear forces are independent of charge. Nuclear forces are independent of charge. So that means simply we will write FPP proton proton and FPN proton neutron and FPN proton neutron, proton proton, proton proton, proton neutron, and this will be neutron neutron. So this force between neutron and neutron will be taken. So this is a charge independent. Suppose after taking net force, after taking the Coulomb forces also into consideration, net forces is F. So we know that so the proton force is less than proton neutron, so which is also equivalent to neutron because in the proton we have two forces, one is attractive force and the repulsive force. So therefore the total resultant is less than that of proton neutron, because in the case of proton neutron only we have nuclear attractive force, and also in the case of neutron also only we have attractive force, that is nuclear force. So that means in the two cases Coulomb forces are absent. Coulomb forces are absent. So in this way, so after that one, so we used to take the next discussion. These forces are generally attractive at a distance greater than 0.8 Fermi. Generally greater than distance of 0.8 Fermi. So we know that 1 Fermi equivalent to 10⁻⁻15 meters. These are attractive whenever 0.8 Fermi. So 2 we can take a range 10 Fermi. Suppose if distance is less than 0.8 Fermi, these values, these numerics are important. The distance is less than 0.8 Fermi, it is repulsive. It is repulsive. And next one is these forces are 50 to 60 times. These forces are 50 to 60 times stronger than electromagnetic forces in nature. Electromagnetic forces in nature. So that is Coulomb electric force or magnetic force. And these nuclear forces are spin dependent. So that is, if the spins are parallel, if the spins are parallel, then the nuclear force is maximum. Then the nuclear force is maximum. Next we will take, so these are saturated forces. These are saturated forces. So saturated forces means they will satisfy easily. So that is one nucleon can attract only the neighborhood nucleon. Only the neighborhood nucleon. So that means actually when we think of this is the nucleus, this is a nucleon, maybe it may be a proton or neutron we are speaking. So it can be interacted with only the neighborhood nucleon, and it may not attract. So the nucleon which is very far away from the original nucleon. So it is satisfied with the neighborhood nucleon. And next we are taking nuclear forces. These nuclear forces decreases very quickly. Nuclear forces decreases very quickly with the distance between the nucleons. The distance between the nucleons. Their rate of decrease. Is much more than Coulomb's law. So that means F is proportional to almost 1 by d power 5. Whereas the Coulomb law, only we have F is proportional to 1 by d square. 1 by d square. So this is the last and important point. Generally, a nucleon is not stable. Generally, a nucleon is not stable inside the nucleus. So that means a neutron always converted into proton, and the proton also always converted into neutron continuously. This is a continuous process. 0 and 1 means neutron. Neutron is converted to proton, that is 1h1, or we will call this as proton, plus pi minus. Pi minus is nothing but It is pi meson, a fundamental particle. So when we think of proton, so that is 1h1, or else we used to call as proton. 1h1 equal to 0 and 1, plus we have pi plus. And so when a neutron, or like this, when neutron is converted into neutron of less energy, we will get pi 0. So actually these are called as, all these are fundamental particles, these are called as pi mesons. Due to exchange of these pi mesons, between the nucleus, they are strongly binded. They are strongly binded with each other. They are strongly binded with each other according to Yukawa meson theory. Yukawa meson theory. So that means this is a theory developed to understand the secret of nuclear forces. So how the proton, even though you are having proton-proton repulsion, how the nuclear force tries to bind the nucleons. So because you can see from here, when a neutron converted into proton or proton converted into neutron, we have the fundamental particles generated. So that fundamental particles having some energy. So that energy will tries to bind the nucleons always. So that is the secret. So that is the generation of pi mesons will be the reason for the nuclear force of attraction. So next we used to think of mass and energy. So the relation between mass and energy, we will think. So actually, according to Einstein, mass is another form of, according to Einstein, mass is another form of energy. Mass is another form of energy. That is, mass can be converted into energy and vice versa. Energy also converted as mass. So here the formulas are very important in applying. We will write E equivalent to mc square. So generally we will use this principle when the mass is given in grams or kilograms. Suppose if we take for 1 kilogram, the energy equivalent to m means 1, c means light velocity 3 into 10 power 8 whole square we are taking. So that equivalent to 9 into 10 power 16 joules. Similarly, if we take for AMUs, for 1 AMU, the energy equivalent to, AMU means atomic mass unit we are taking. So that equal to 1.66 into 10 power minus 27, that is the mass. And the light velocity is 3 into 10 power 8 whole square. So by substituting them, we will get 931.5 mega electron volts. So this is the mass energy. And we have mass defect. So we have mass defect. So mass defect means it is the difference between mass of nucleons and mass of nucleus. So mass of nucleons means theoretical mass. Simply we will remember it as theoretical mass. Delta M, mass defect So we can symbolize the mass defect as delta M. So that is equivalent to, simply we will memorize like this. This is the difference between theoretical mass. Theoretical mass means how many nucleons are present and what are their masses. We will multiply with each other. Theoretical mass and practical mass. Theoretical mass and practical mass we will do. So theoretical mass means, so we will take Z into MP plus A minus Z into Mn minus M, we will say. So that is the theoretical mass and practical mass. This mass defect exists in the form of energy. In the form of energy, which binds the nucleons. Which binds the nucleons. So generally, that's why we used to say the definition of binding energy. Binding energy B equivalent to delta M into C square. So this is joules. So whenever you are interested to express the binding energy in joules, we will use delta M C square. So here delta M should be in kilograms or grams. Kilograms or grams we will take. And we will write that binding energy equivalent to, we will write delta M into, so that is 931.5 MeV. So this will be the possible whenever the mass defect is in atomic mass level. And also we will see the binding energy equal to, we will write Z into MP plus A minus Z into Mn minus M. So instead of delta M we are writing, so this is into 931.5 MeV. So in both the cases, so here also mass of proton or mass of neutron, they should be expressed in AMUs. And here the important pointing is binding energy is not the measure of stability. So it is not the measure of stability. Binding energy is not the measure of stability. But we will say that the binding energy per nucleon is the measure of stability. The binding energy is not a measure of stability, but we will take the binding energy per nucleon is the measure of stability. So therefore, we are writing binding energy per nucleon. Binding energy per nucleon, we used to call this is the bar, that equal to B by A, that equivalent to delta M into C squared by A. So whenever you are writing energy equivalent to MC square, so we will write in the form of joules. So this is very important. And after discussing about the binding energy, we used to think of the curve of variation of binding energy. Variation of binding energy per nucleon with mass number. So variation of binding energy per nucleon with mass number. So first we will understand how to plot the curve. So on the y-axis we are taking binding energy per nucleon, which is generally expressed in mega electron volts. And on the x-axis, we will take mass number. So that is capital A on the x-axis. So here we are going to see a graph. So which is almost similar to a straight line, and we have some ups and downs. So where you are having maximum energy for iron decreases. So when we think of uranium-298, so it is having an average energy. It is in the order of 7.6 MeV. So let us discuss it a while. So here I am taking, this is the lithium-6, 3 lithium-6. And this is the position for the helium-4. And this is 14 nitrogen. This is 12 carbon, 16 oxygen, and 13 oxygen. So 56 iron. So here we will understand so of various binding energy per nucleons of the system. So when we think of uranium, this is very important, 7.6 MeV. And for the case of iron, generally this is maximum. So it is having a value 8.8 MeV. So this value. So this binding energy per nucleon value is 8.8 MeV. So now we will analyze this graph. So what the things you are going to understand from the graph, let us see. Actually, the first point we are taking is binding energy per nucleon. So binding energy per nucleon increases rapidly initially. And the curve possess, so we will see some peaks. The curve possess peaks corresponding to so we will see some peaks like helium-4 and 12th carbon, and as well 16 oxygen. They have more binding energy per nucleon. They have more binding energy per nucleon. Sorry, they have. So in the graph, let us see 3 lithium-6 and 7 night. 3 lithium. We are having 2 helium-4 and 6 carbon-12 and 8 oxygen-16. They have more binding energy per nucleon. So therefore, they are more stable. So they are more stable. We will see that they have even number of nucleons. But from the graph, if we observe, suppose we take 3 lithium-6 and as well as 7 nitrogen-14 and as well as 8 oxygen-13. So there they have less binding energy per nucleon because they are at the bottom of they are in the valleys. You can see 3 lithium-6 position, 7 nitrogen-14 and oxygen-13. They are at the bottom of that valleys. So they have less binding energy per nucleon. So this is a comparison between only those 6 elements we are taking. So they are less stable. they are less stable because they have odd number. They have odd number of nucleons. They have odd number of nucleons. So this is also one important point. And the second one, so we will see that when above the mass number 20, when above mass number 20, so binding energy per nucleon increases gradually. So it increases not rapidly, it increases gradually. So that means you can see here, from here to here, from here to here, so it increases gradually. Binding energy per nucleon graph increases gradually. And in between 40 to 120, mass number, in between 40 to 120, the curve becomes flat. The curve becomes almost flat. You can see from the curve. Suppose if this is the 40, so from 40 to 120, almost the curve is like a straight line. And so this is very important point. The average binding energy per nucleon. The average binding energy per nucleon. The average binding energy per nucleon is lied in the range. Is lied in the range of 8.5 MeV. 8.5. And we will see that from the graph for 26 iron 56, 26 iron 56, binding energy per nucleon is maximum. Is maximum. And this is in the order of 8.8 MeV. So these points should be memorized. So these are very important. And we will see after mass number 120, after mass number 120, binding energy per nucleon decreases and drops up to 7.6 MeV per uranium. You can see it in our graph. So you can see, so whenever it crosses the 120 point, whenever it crosses the mass number 120, so automatically we will see that the binding energy per nucleon gradually decreases and becomes minimum, it is just 7.6 MeV. And it is maximum for iron 26, 56. So we are taking, so these points. And the most important conclusions are, so we will see here the lighter, all these are lighter elements. Lighter mass elements are not stable and the heavier elements are also unstable. They are not stable. So actually, let us see what happens is to get stability. To get stability, lighter nuclei undergo nuclear fusion. To get stability, lighter nuclei undergo nuclear fusion. So that means in the graph we will see. So that means to get stability, all these nuclei up to 40, all these nuclei, so they will undergo nuclear fusion. And we will see the more heavier particles, the more heavier atoms. So they will undergo nuclear fission to get stability. So that is the thing we are writing here. To undergo nuclear fusion, so the lighter nuclei, and to get stability, these heavier nuclei undergo they undergo nuclear fission. And to get stability, heavier nuclei emits alpha and beta particles. Heavier nuclei emits alpha and beta particles. So after thinking of this binding energy per nucleon graph, so we will see packing fraction. So we will write packing fraction. Packing fraction can be symbolized as F. Small f is equivalent to mass defect by mass number. And from the experiments, it is observed that F is very large. For lighter nuclei, F is very large for lighter nuclei. Suppose if we take 1H2 and 1H3, 1H2 and 1H3. Actually, we have a graph. So from the graphs, we can easily understand the relation for the packing fraction. So it is observed that the packing fraction decreases with the mass number. So this is the packing fraction, and this will be the mass number. And we understood that as the mass number increases, from the graph you will see as the mass number increases, so the packing fraction F decreases. It is evident from the graph, F decreases and becomes 0. And becomes 0 for 18 oxygen, 16. So that is, so this 16, we will see that the packing fraction equal to 0. And for the mass number in between 16 to 180, so this is 16 and this point is, let us say, 180. So these values are absolutely important. So the packing fraction is negative. The packing fraction is negative. So when the packing fraction is negative means, so definitely these nucleons are strongly bounded to nucleus. They are strongly bounded to nucleus. And for mass number more than 180, F is positive. So that is after this. So we will see that the graph is going to be positive. F is positive. And we will see most of the nucleus with mass number more than 235, mass number more than 235. So they are unstable.